who were not present during my previous lecture, and for those who were asleep, I will summarize what I said in a few sentences. And this will be the starting point. If I have chalk, must be somewhere. I argued that it is convenient to define the following vector field, complex vector field, which I named some years ago Riemann-Silberstein vector, which is built from the electric displacement vector, properly normalized, and from the magnetic counterpart, magnetic induction to mu. This formula, of course, in vacuum means that these are vacuum values, but it is also possible to take this in any uniform medium, dispersionless medium. This complex field, it's a function of space-time, satisfies one single equation, which is obtained from the Maxwell equations, of course. And this equation reads time derivative times I is something acting on F. So it is similar to the Schrödinger equation, and some people think that this analogy should be explored, and we will talk about this later when I talk about the quantum counterpart of this theory. Then, of course, there is also the condition that the divergence of F is 0, which almost follows from this equation. If we take the divergence on both sides, then it only says that the divergence is time independent. Now I will start working with this vector, and we'll show you that many things in electrodynamics become very, very simple within this framework.
But that holds only when there are no charges.
Yes, this is free.
This is completely free
theory of electromagnetism. About charges, this is something I want to just say. Well, these equations are obviously invariant under the following transformation. F is multiplied by some phase phi, say F. We just multiply by a phase factor, which is a constant, does not depend on space and time. Now this transformation, when written in terms of D and B, or I will, in vacuum, I can also use E and B, results in a kind of a rotation. I take the real part, and the real part tells me, let me just write it in terms of E and B in vacuum. So E prime is equal to cosine phi times E minus sine phi times B, and there's a factor of C needed here, otherwise the units will not match. Now B prime is B, cosinus phi times B plus E over C sine phi times sine phi. Okay. Now this is called in standard electrodynamics a dual rotation. And the dual rotation is a symmetry of this equation, and it is the symmetry of Maxwell equations. there is some interesting philosophical sort of question that one may ask. As Professor Tulski mentioned, there are charges also. And charges break the invariance because electric charge density appears in the equation for D. So we cannot rotate now D and make it into something which is a combination of D and B, because there are no magnetic...
Unless there would be a magnetic
No,
charge.
that, again, that would not be a symmetry, because magnetic charge will have some value, it will not be invariant.
If I relabel rho and...
No, it wouldn't work. Ah, if you change charges, not
Charges, if
Okay.
if
the
the magnetic and electric charges
Yes,
satisfy some
I'm
condition.
coming to that. Well, the question is this symmetry breaking universal in the whole universe all the time, or perhaps this symmetry breaking might be changing during the time evolution of the universe. Let me make a picture of that. This is symbolically the E and B plane. Now, in this E and B plane, we select a certain direction, and we call it the electric direction, because the charges were named electric charges. We could equally well say that, these are not electric charges. Electron does not have an electric charge, it has a magnetic charge. And everything would work, except that instead of this equation, we would have to write the equation divergence of B equals rho. When would this symmetry breaking really be relevant? Of course, if we could somehow compare two situations. One situation, let's say, is our world, where we fix this and call this the electric direction. And could we compare this with other worlds, say distant galaxies, where this direction is different? Well, it turns out that this is a very difficult job, almost impossible, because when we see light coming from this distant galaxy, then what we see is a plane wave coming, practically. Because even if we had two observation points which are separated, say, by 1,000 kilometers on Earth, it still would be almost nothing. The angle would be extremely small, and therefore the difference between the wave that was emitted by an electric dipole and the magnetic dipole would only differ in the orientation, and we cannot say what was the orientation at the source. So this is a philosophical remark, and now let's proceed with other properties of this vector. This analogy with quantum mechanics, that this looks like Schrödinger equation, is continued when we consider important physical quantities. What are important physical quantities for the electromagnetic field? The energy, the momentum, or the Poynting vector integrated angular momentum. We can write down the formulas. What is the energy? The energy, when you express the energy in terms of this complex vector, it turns out that it will be, not surprisingly, F star F scalar product. Very simple formula, and it is, of course, the same as the standard formula where you have d squared plus b squared properly normalized here. So the energy looks like something we know from quantum mechanics, psi modulus squared, except that this is the energy, not the norm. And this is a source of very important problems.
But it is also conserved.
Of course, this is
So
conserved.
that's also the philosophical, we can call
Now
it.
we have momentum, and momentum is one over IC. Momentum is always energy divided by speed of light. V3R F cross F. Vector product of F.
That explains why there is
looks nice.
And that's why the I comes also.
And this is why I, because this is imaginary.
Yeah, because you like.
Then we have two other important quantities. One, perhaps more familiar, and this is angular momentum. What is angular momentum? Is the arm multiplied by momentum. So the arm is R, and momentum is the same 1 over IC F star cross F. We take this momentum and we multiply by the arm. There's one more quantity which is relevant for relativistic considerations, and I call it N, and this is simply the following integral, R multiplied by the energy density. What would that be in common terms? This is just the first moment of the energy distribution. Now this quantity is not a constant of motion because the energy distribution is moving. So when you differentiate with respect to time, you find that this is proportional to momentum. So these are the important quantities, and we will talk about these quantities a lot more when we come to quantization later, and also even today within the classical theory.
But
yes,
it has the same problem that it depends on R, the way how I choose the vector.
of course it depends on the origin of
The coordinate.
the first moment depends where you start counting. Okay, so these formulas will be still useful, and now
And what happens with the second moment, R squared F?
second moment can be calculated, and it changes linearly with time because waves spread out.
Oh. So it's a kind
Maybe
of a
at some
spread
point-
factor, right?
Maybe at some point I will give this calculation. It's similar to the fact of spreading wave packets
Yeah, so that's
in
the point.
mechanics.
That's the, yeah, well,
In quantum mechanics,
Mechanics.
yes. This analogy is... Okay. So, one more observation. Perhaps it should have been made on this blackboard or green board. Namely, what is F squared? We encounter F star F, but let's take just plain F squared. F squared is a complex object, and it has two parts. One is expressed in terms of E and B, E squared minus B squared, and of course there is some epsilon here, which I will omit. It's not important. And the imaginary part, which is again up to some constant factor, E dot E. The real part is an invariant, one of those two invariants in relativistic electrodynamics. This does not change under rotations, obviously, but it also does not change under Lorentz transformations. And the same here, this pseudoscalar, the scalar product of E and B, is a constant under Lorentz transformations. If so, if this is invariant, that means that if we apply a Lorentz transformation or a rotation, That means that f transforms, it's multiplied by a certain constant matrix times f, and this matrix must be such that the square is constant. So such matrices are called orthogonal matrices if they don't change the length of the vector. A generalization here is that we are talking about complex orthogonal transformations, but the mathematical equation is the same. The matrix O transforms times the matrix O is a unit matrix. This is the definition of an orthogonal matrix. As I said, the only extension of this concept here is that we are talking about complex. And one can find out, if one is patient, from Lorentz transformations of E and B, one can find what this O is really like, but that I leave as an exercise. And now, let's go further and try to make use of this whole formalism. Now, the first thing that I will do is to go from f to the Fourier transform of f with respect to space leaving t. This is the Fourier transformation. I can write the formula. The formula will be that f of r and t is equal d3k, and usually there is a convenient normalization to pi to the power of 3/2 e to the I kr. That's the definition of the Fourier transform, times f. I will not distinguish between this f and this f, except I will write different arguments of the Fourier transform. If you want, you can put some tilde over f. Now, f of k, let's go back to our equation, satisfies the following equation. On the left-hand side, we have the time derivative of f of k and t. On the other side, we have the curve, but the derivatives under the integral sign bring down k, and I now is cancelled, so the equation for the Fourier transform is an algebraic simple equation, and we can find easily all solutions of this equation. So the first observation is that f, of course, because this is a transverse vector, that it is lying in the plane perpendicular to the vector k. Therefore, f, in fact, has only two components in the plane perpendicular to k. So in order to write a solution, it's sufficient to choose two independent vectors, and it will be convenient to choose a complex, because this is all, of course, complex, to choose two complex vectors. And I will choose these vectors, E of k, call it plus, and E minus of k. These two vectors span the space, two-dimensional space, and the amplitudes now that are multipliers, here is f of k. T is equal to E times some alpha plus E minus alpha minus, and of course alphas are functions of k and functions of t. So we have alpha plus minus function of k and t. Substituting this into this equation, we arrive at the following equation for the time dependence.
E are unit vectors.
Not necessarily, but it will be convenient to make. I will give an explicit formula in a moment. Yes, yes. they will be assumed to be normalized. So we have this equation, and this equation means that the time derivative of alpha, I substitute this formula into this equation. On the left-hand side, I have time derivatives of alphas, and on the right-hand side, I have, okay, let me write it down completely so we will not make mistakes. Alpha plus times plus, it's a simple calculation, but it's better to do it explicitly. This is equal to K cross, and the same combination, alpha plus E plus alpha minus E minus. And now what happens to K plus and K minus? I have not said anything yet about these vectors except that there are two independent vectors. So of course it's convenient to make them orthogonal. And therefore, this will be the assumption. And just to be very specific, I will write down my preferred formula for E. For E plus, which I call E, okay. And the formula has the following form. As Professor Tulski mentioned, it's better to normalize them. So here is the normalization vector. 2k. K is the length of the vector k. Kx squared plus ky squared. And here is this matrix. One-dimensional matrix, which is minus kx kz plus ik ky minus ky kz minus ik kx, and here is kx squared plus ky squared. Sometimes I forget whether it's minus sign or not. No, it's plus sign as I read it. Okay, so this is an easy check that these are orthogonal, that this is a vector, I'm sorry, E minus will be equal. Conveniently, this will be E star complex conjugate. This will help. This is not necessary, but it's convenient for further development to assume that these vectors are related by complex conjugation. So we have E plus, we have E minus, and now we can see for this particular choice, when these vectors are orthogonal, what are the results of multiplying k by E plus minus, and it turns out that this is minus plus k, the length of the k vector, times E plus minus. In other words, you may say that these vectors are eigenvectors of the cross product, of the vector product. If you take vector product, you get a number, the length of k times, I'm sorry, I. Now one may say something must be wrong because this is orthogonal to k, the left-hand side, orthogonal to E, and the right-hand side is just along E. But for complex vectors, it's all right. All you can deduce is that by multiplying both sides by E plus minus, on the left-hand side we get 0, and on the right-hand side we have E plus minus squared equals 0. complex vectors. Because when you split this vector into the real part and imaginary part, you get two conditions. The real part must be 0 and the imaginary part must be 0. The real part means that the length of these two vectors, the real part and imaginary, must be equal. And second is that these two real vectors are orthogonal. So that much of this Kishan properties, but in physics sometimes one has to go through these specific examples just to understand what's going on. These vectors, even assuming their orthogonality, are not fixed because you can always multiply them by a phase factor. Now this is a particular choice of the phase factor, and you will see later why this particular choice is very convenient. Okay, so we now go back here, and using this property of K, we see that the time dependence of alpha plus minus is the result of the following K times C something, you didn't correct me. There is this factor of C there. Okay. So this is K times C times alpha.
We assume that C is equal to 1.
No. I don't like this because it's very convenient to check from time to time whether dimensions on the left-hand side match the dimensions on the right-hand side. So the solution of this equation here is very simple. Alpha plus minus depend on t as e to the, let's say, kt. This is e to the minus plus I, this is called usually omega, I omega t times alpha plus minus k only. This is the dependence on time, and this was to be expected. Therefore, we can come back to our equation, and since we know now the time dependence, we can write down the formula for our wave function, and I will do it after some slight changes for convenience. You see from this calculation that there are two terms. One term that depends on minus I omega t, and the other term that depends on plus I omega t. So now I make the following observation, which follows from this formula, but it is again a convention which is making life simple, namely that E of K star, complex conjugation, is equal to E of minus K. Because the only place where the imaginary unit enters is here, and this is the only part that changes sign under complex conjugation. And that makes it possible to write this integral, these two terms, in the following form, and this will be the final result of what I want to do at this moment. Namely, we have d3k 2 pi to the power of 3/2. And now I will write something which at first you will find hard to believe. Remember, we had two vectors, E plus, E minus, and I now write one vector, and here's some amplitude f plus of k, which replaces this alpha, e to the minus I omega t plus I kr, plus the the second term, f minus, of k, and it is convenient for our future investigations to name this complex conjugate amplitude, although at this moment it is just a matter of convention. E to the plus I omega t minus I k r. And as I mentioned, you at first may say that there is some mistake here, because before we had just e to the I k r and two vectors, and now we have here minus I k r. It's simply change of the integration variable. In the second term, it is convenient to replace k by minus k, and the integral, of course, does not change. And what is the result of this change? Namely, we have the second vector, and the second vector became e of minus k, and I changed minus k to k, and this is the result. And this, in a way, stresses the convenience of using this description of the electromagnetic field, because somehow we have just one polarization vector to worry about, and some people could not swallow this. A referee of one of our papers on that subject complained that there must be something wrong, because we know that there are two polarization vectors, and these authors are missing half of the electromagnetic field because they only consider one polarization vector. But I hope that you do understand what is the origin of this. The origin is that this does not work for a single amplitude. There are two vectors. But when you have integral, then you can change the integration variable. And that's what this is now. Let's look at it for a while. This is the most general electromagnetic field expressed in terms of Fourier amplitudes. There are two Fourier amplitudes, two complex Fourier amplitudes, which means that there are four real functions. Four real functions describe the electromagnetic field. Let's count this from the point of view of straightforward Maxwell equations. We have Maxwell equations for two vectors, two three-dimensional vectors. So we have 6 degrees of freedom. Now we reduce this to 4 because we have divergence conditions.
Yeah.
Two conditions, the divergence of D is 0 and divergence of B is 0. These two conditions restrict the number of degrees of freedom to 4 only, to 4 real degrees of freedom. It will turn out that these are functions that have simple interpretation, but before I do that, I think I need more space, and for that I will sacrifice some of our previous formulas, keeping those that are still relevant. So I'm erasing this part. And now what is interesting is to express our physical quantities in terms of these amplitudes. And then we can have kind of interpretation of these amplitudes also. So let's first do the energy. This is the energy in terms of the space-time functions. And how does it look in terms of, well, the factor 2 pi to the 3/2 is conveniently chosen to get rid of this factor in this formula, and there will be just a straightforward integration over k. Here, what I'm writing now, here is the result of what is called in standard Fourier analysis Parsable Theorem. Parsable Theorem means that the integral of the original function is equal, modulus squared is equal to the Fourier transform modulus squared. So Parsable well, formula now. It's for these vector functions, and it has the following simple form. Namely, we get, you see, since the vectors E are normalized, when you take the norm here, you get nothing but f plus of k modulus squared plus f minus of k modulus squared. However, just to make the analogy useful for future considerations, I will write this in an equivalent form, namely sum over lambda, f lambda of k. Lambda takes two values, plus and minus, star times f lambda of k. Looks familiar. This is something that we know from quantum mechanics. But where is the energy here? Well, the energy comes in a rather tricky way. Something is missing here. No, I think it's okay. Namely, nothing prevents here the following change. I will divide by omega and multiply by omega. So I will have lambda f star of k. Lambda omega here and f lambda of k. So this is something like expectation value of the energy. If we remember Planck's formula, there is no h bar here because I'm now at the classical level, but later I will introduce h bar here. Anyway, the analogy with quantum mechanics is here such that this looks like the expectation value of the energy, missing this factor of h. But why omega appeared in the denominator? This is because we are talking about a relativistic theory, and the integration over k is not invariant under Lorentz transformations. Of course, d3k is invariant under rotations because this is just the volume element. If you rotate the volume element is the same volume element. However, when you go to a moving system, when you replace k by a change vector because of the motion, Doppler effect you may say, then this will change. It so happens that dk over the modulus of k is invariant. This is invariant. And what is the simple way of proving that this is an invariant? It goes as follows. I have the integral over d3k over k. And I can write this down also in the following form. I integrate over all four components of k, but the time component is fixed. So how to fix the time component? The time component is fixed if I say that k squared minus k0 squared here is the argument of a delta function. This fixes the value, provided we also say that k0 is positive. Now the delta function has the property that if you have a function under the delta function, and this is the function of k, then the trick is to get rid of this delta function and divide it by the derivative. And this derivative brings down k, because the derivative of k squared is twice k. 2 is not important for this analysis. And this is the origin of k. This is clearly an invariant object, because this is the invariant length of the vector in relativity, and the four-dimensional volume is invariant under Lorentz transformations, not to speak of normal rotation. So this is something that is worth knowing, namely that this formula here makes some connection. And of course, the next question is, what about P? Well, P will be d3k over omega, but since there is an additional c here, we have just d3 over k, and here we have sum over lambda. This is the result of the calculation. I'm not here doing some assumptions. I'm just substituting my Fourier transform and laboriously evaluating this Fourier transform. It takes some doing. You must write down the formula for the cross product of E star and E, but this is simple algebra. And the result is F star K here. The expectation of K. Again, if I wanted to make analogy with quantum mechanics, I will put H bar, and this will be the momentum of the photon, and this will be the subject of some future considerations. Now the hard part, not so hard, but it takes some doing, is to write down the formula for the angular momentum. Well, this is not quite trivial, and it is important for many future purposes. I will use this formula, F star of K. And what enters here is some kind of an angular momentum operator, if we want to use this analogy. And what is the form of this expression? Well, it goes like this. K cross product, let me get this with all signs correctly. Yes. And here is minus or 1 over I, let's say. D, what I call D vector, and this will be defined in a second. And that is then augmented by second term N and F. Let me now explain all these symbols. This is easy. N is the vector in the K direction. So one would call this the part of angular momentum, which is connected with the spinning motion of the electron. And again here, we see the simplicity of using these polarization vectors in the complex form, because otherwise, if we use a different basis, it will be some messy formula. Here, it's just for one amplitude, for lambda plus, we have positive contribution to the angular momentum, and for lambda negative, there's negative. So the photons, as we know very well, may have angular momentum right-handed or left-handed, and that is the sign of lambda. And the sign of lambda means which part of this expression it comes from. Now, what is D? D is a vector operation, which I will write as normal partial derivative with respect to K vector, minus I lambda and some vector alpha dependent on K. Now, there is some profound physics.
You should also have a lambda in the, if lambda is the same lambda as
The same. Where?
well, because lambda is plus and minus.
Here.
So in the
Yes, I agree. Now this is, let's talk about this part. This part is nothing else but the Fourier representation of the standard angular orbital angular momentum in quantum mechanics. K times the derivative. In Fourier space, everything is upside down, so K is the momentum, and the derivative with respect to momentum is position. So this part we understand. Now this part is tricky, because alpha is not a physical object. It depends on the choice of the phase of the polarization vector. If I change the phase, alpha transforms, goes into alpha, plus derivative of the phase with respect to K. So this looks like a gauge transformation, and it has some similarity with gauge transformations. And this similarity is already seen here. Since E of K is defined up to a phase factor, that means that F of K is defined up to a phase factor. If we treat this as a physical object, in order to have the same physical object, if we change the phase of this, we must also change the phase in the reverse direction to make the whole integral not changing, because F is a physical measurable field. So this dependence on the phase is of the same origin practically as the phase dependence of the wave function in standard Schrödinger wave mechanics. But that's the way it is. And one remark that should be made here is that this decomposition here is not dependent on this phase, because one part can be defined as the part which is orthogonal to K, and this is the part which is parallel to K. And this is a very important information, that the photon, which will come out from here, has these contributions to the angular momentum. The photon has orbital angular momentum, and it has an additional part which is always along the momentum. This does not translate too well into space-time picture, because when you go from wave vectors to R, then this here, N, notice, is the length of the vector. The length means that we divide by K. Division by K in space is a non-local operation. It is some kernel, etc. Therefore, the separation of the angular momentum into two parts is easy in momentum space, but it becomes awkward in position space. Of course, one can write a similar formula for N. I will not do this, it's in our paper. There will be the same D entering this. And one more remark about D. If this is the analog of a potential, then what is the analog of the field strength? Well, the field strength is the curl of the potential, and when you do the curl, then the curl, of course, will not change under this, and the curl turns out to be a vector which is along the K direction, proportional to K. And there is a lot of physics here that goes by the name of Berry phase, which can be derived in this setting. Now, so this is about the general structure of these fields in momentum space. And now, to make you familiar with all these concepts, I will talk about specific examples. Specific examples are to make life transparent. Before I go to specific examples, which will be discussed next time, I will set up a general framework, how these specific examples will be constructed. Of course, one way to construct specific examples is to solve Maxwell equations. And this is an awkward job.
That will be a general form of a specific example.
Yeah. we have a general form of Maxwell equations, and then we must find out what are the solutions of these equations. And it takes some effort because we have 6 equations and we have to use them all to find the solution. There is a very simple method that goes back to Sir Whittaker. Whittaker was a mathematician, a physicist, also part-time. I would say he hated Einstein. He wrote a very interesting 2-volume monograph on electromagnetism and relativity, and he claimed that all what Einstein did was to repeat what Poincaré did before, which is not true. But that was Whittaker. But he was a smart person, a very good mathematician. Among other things, he also wrote this monograph with Watson on analysis, where there are many interesting formulas.
They also wrote a book on the Bessel functions.
But that Watson, Watson, not Whittaker.
Yeah, the Watson.
The Watson Bible.
Do you remember what is the first chapter in the book of Watson on Bessel function? What is the title?
No.
It's the Bessel functions before a January uprising in Poland. Because it's a Bessel function before 1860.
I see. Yes, he was, and he noticed one thing, that one can generate solutions of Maxwell equations. He did not know in those days about the Riemann-Zilberstein vector, so he took ordinary normal Maxwell equations, and he realized that one can construct solutions of Maxwell equations from solutions of wave equation. Wave equation is also called the D'Alembert equation, 1 over c squared dt squared minus Laplacian, acting on some function chi psi over P, is the wave equation. And Whittaker noticed that if you have 2 such functions, then you can construct solutions of Maxwell equations by pure differentiation. Now, there is a tremendous difference in difficulty in solving partial differential equations. Mathematica can hardly do it, and if you just try it, it will be
independently of the boundary conditions?
No, in free space.
Ah, in free space.
Free space. Let's not be too demanding.
Yeah, but
so if you have
we need the solutions of the free Maxwell equations in various geometries.
No, we most often need the description of electromagnetic waves. And electromagnetic waves
unless you want to solve the resonators.
I don't want to solve the resonators.
Yeah, but that's what is used for in electrical communication. Resonators. Who cares about the cable?
Of course not resonator. You have a running wave along a fiber.
You want to listen to them, and I cannot listen. You have to have a device to catch them.
Yes, so what?
And this is something like a resonator.
No. Okay. So Whittaker noticed that given 2 solutions, kind 1 and kind 2, of the wave equation, one can find the corresponding solution of Maxwell equations, which is a great simplification because it's much easier to work with these scalar functions than to work with 2 vector fields. And of course, most mathematical analysis of electromagnetic beams very often uses only the scalar description of electromagnetic field. One people say that this is just the X component of the electric field, and then this is studied. But here we have a very precise mathematical constant given two solutions. The wave equation construct a solution of Maxwell equation. Now we have a complex object, so now an obvious idea is to generalize in a trivial way the Whittaker idea and to have just one complex function phi and generate from this one complex function the solutions of Maxwell equation. For example, if chi of RT is a plane wave, we use the construction and we get the solution of Maxwell equations, which would require some doing. Not to speak of the present day possibility that we can use Mathematica, which can easily differentiate anything, almost anything, which is given in a functional form, and the integration of partial differential equations is a different level of complication. So I will leave you at this point because I'm running out of space on these boards, and the Whittaker construction would require more space to use.
There is a war.
And next week I will show you how this construction is made and what are the benefits of this. Thank you very much.